Okay, everybody, welcome to class. Hope everybody had a phenomenal fall break. Who traveled the furthest from home? To Boise? Boston? That's pretty far. That's where I went over the fall break. Yep, I was in Boston. Anybody travel further than Boston? The 9th? Magical. All right. Okay, we're going to dive back into chapter 4. We'll probably finish polymers today. Our goals are the following. We already talked about Bakelite and nylon 6,6. We're going to review those and show you a demo. We won't do it because it smells horrible, but we'll show you it. We'll talk about a few others like PET and polycarbonate, and then we're going to get to the latter half of this chapter, which is talking about things like molecular weight. How do we quantify? We know that these things can be long chains or short chains. How do we quantify that? We do it with something called molecular weight. We'll differentiate between thermoplastics and thermosets. We'll talk about how different configurations, if you can rotate these things in different ways, or if they have long or short side chains, what does that do to the properties that we might care about? And then finally, we'll talk about what does it mean for a polymer to be crystalline or partially crystalline, okay? So if you remember last time, we were talking about some old school polymers, and then we got to nylon 6,6, and somebody remind me, why on earth do we call it nylon 6,6? Where did the 6,6 come from? Yeah, there's 6 carbons right here. If you count these things, that's 1, 2, 3, 4, 5, 6, and then an amine group. And then it's got another 6, 1, 2, 3, 4, 5, 6, and then another amine group. So hence the carbon 6,6. When you make this thing, you can make it via copolymerization. So instead of polymerization, which we talked about last time, we've got your monomer. It typically has something like a double bond, and you introduce a radical, something like a bromine ion or a chlorine, something that's going to attack that double bond. When it attacks the double bond, it steals an electron, leaving one just hanging electron, which is a free radical. That attacks another monomer and so forth. So this can happen with a single monomer, or you can have multiple monomers. We call these copolymers. And nylon 6,6 is an example of a copolymer because there's 2 monomers, right? There's this monomer, which has like the double bonded O's on it, and that's different than this monomer. And if you get those alternating, then you end up with nylon 6,6. And so what's cool is you can actually make this happen. Again, we're not going to do it because it smells awful.
Which did not exist before 1930.
So here they're starting with, if you see here, you've got 2 different monomers on the left and right up there. This first one is a adipoyl chloride, and then this is hexamethylene diamine. So this looks like the second half of it. It's got the amine groups on it, and it's got the 6 carbons. Whereas this one, it's got the oxide, right, double bonded, but it's got chlorines on the end. So if you put these 2 things together, they're going to bond to form that. But when you put them together, they actually phase separate at first. So this is looking at both of those 2 monomers. They're both liquids. You put them in a beaker, and they phase separate, right? So I think this is the chloride, the adipamide, and this is the other one. And right at the surface where they're touching, that's where you're going to form your polymer, right? Now, what they do that's pretty clever is they'll reach in here, they're going to grab that interface, and they're going to start to pull it out. As they start to pull it out, this is a solid polymer that forms. So you're pulling the solid out, and you're exposing a continuous new layer of monomer that can be in touch with one another, right? So let's take a look at this.
2 layers at the interface. This is called interfacial polymerization. This is the nylon rope trick. As previously explained, the nylon is steadily collected from the interface of the 2 solutions. While the nylon rope trick is not how nylon is produced within factories, it is an excellent way of demonstrating the synthesis of a synthetic polymer and interfacial polymerization. Plus, it looks really cool.
But if you keep on drawing that, this is what it looks like if a bunch of high school kids do it. It looks pretty gross and terrible. But if you grab that interface really precisely and you pull it at a different speed, you can change the thickness of that diameter that forms, right? So they call this polymer drawing. You draw it out of the solution, and you can get really thin versus really thick fibers. But this is how you make a long, continuous fiber. Remember our problem with carbon nanotubes? We'd love to make one as long as from here out to space, but we don't have a good way to do that. We do have a good way of forming really long polymer strands. Yeah, question?
So why does it smell bad then?
It's an amine, and amines always smell bad. Nitrogen bonded to hydrogen smells bad. Yeah, and this is amines, so it just smells awful. It's a little bit toxic. If we had a fume hood, we could do it in here, no problem. Okay. Any questions on copolymerization, how that would work, how you would draw that into a fiber? Okay, let's keep going. So 2 more polymers you should be aware of. One is PET. This is the stuff that many bottles were made out of. But to make this and make it not totally brittle, they were adding a plasticizer, bisphenol alcohol. There's concerns about that being a carcinogen. So now you'll see regularly all sorts of Tupperware and bottles saying BPA free. The BPA is your bisphenol alcohol. So PET is hard to make if you take out the BPA, so they're looking at alternative materials, or at least alternative plasticizers. That said, look at the monomer here. The monomer is you've got a benzene ring along the chain. So instead of the chain just being carbon-carbons with the zigzag that we've come to know and love, you can put all sorts of crazy things in there, like a benzene ring right in the middle. This is a pretty strong molecule. These are all, double bonds are stronger than singles. This is why PET, old Nalgene bottles, were basically indestructible. They were really, really strong. They were pretty crack resistant. PET remains a pretty good material. It's a good glass substitute. 60% usage is for fibers, 30% for bottles, and it's just a great substitute for glass because of its strength. Then you've got polycarbonate, another good glass substitute. This has 2 benzene rings, right? It's got 2 methyl groups coming off of the carbon in the middle. You've got an oxygen along the chain. This is another strongly bound material. This is very high impact resistance. Impact is right, it's going to be its shatter resistance. This is what they make bulletproof glass out of, right? Is polycarbonate. So bank windows that have that thick glass is probably polycarbonate. You can make it out of other things, but it's probably polycarbonate. Interestingly, it has really good fracture resistance. It doesn't break apart easily, but it is pretty easy to scratch. And they made CDs out of this for a long time. And if you grew up in the era of CDs that were scratched, it was because of this material. It was great in that it wouldn't fracture, but it scratched pretty easily. And so they actually started putting a hardening layer on the top of the CD to prevent it from scratching as easily. And then we just quit because we found better ways to store data. Okay, so let's talk about molecular weight. When you put all your monomers in the vat, you introduce a little bit of an initiator, like chlorine or bromine, something that's going to get the reaction happening. You might have one chlorine atom over here starting to form a chain, and another one over here. To link up, they now have no reason for it to keep on growing, because there's no more double bonds they can break. Or in other words, if you had your bromine, which had its free radical, and it found something like this ethylene monomer, right, which had hydrogens like that, it attacked the double bond and it formed bromine bonded to this, with now single bonds everywhere and the free radicals over there. As soon as this guy makes another one, it's going to be terminated, right? It'll be, and that might happen at a short length, whereas other ones might go a much longer distance before they run into something and could be really long. So it would be wrong to say that when you synthesize polymers that they're all going to have the nice same length of fiber. That's not what's going to happen. In fact, there's typically a distribution. And the way that we think about the distribution is in 2 different ways. So if you look at the amount of polymer versus its molecular weight, we can determine it 2 different ways. One is based off of the length, the number of mer units, right? We could add up how many of these little C2H4 units are there. Is there 100? Is there 200? Is there 1,000, right? Or you could do it based off of the total molecular weight of the entire molecule, okay? So you'll see M sub N and M sub W. M sub W means that you figure out the molecular weight based off of the weight of these molecules. And M sub N means you're doing it based off of the number of repeat units. Yeah, question?
So amount of polymer, is that measured by
Yeah, you can do it by weight or by volume or by moles, right? Practically speaking, in industry, they do it by weight. When you separate these things, there's tools for doing that. I think viscometry is a pretty common way to do it. How do you measure viscometry? Anybody have, what is viscosity? We talked about that yet in this class? I don't think we have. What's viscosity? Yeah, like the flowability of something. Like motor oil comes in different viscosities, right? And depending on the type of car you have or the environment you're going to be in, you want thicker or thinner motor oil. Well, they can do that by changing the molecular weight. Turns out the viscosity and molecular weight are pretty closely related. So what they can do is they can take a little spindle and they drop it into your fluid of polymer if it's molten, and they spin this spindle, and they measure how much resistance is on that spindle as they rotate it. And as they spin it at different speeds, you can basically figure out what weight fraction of your polymers are different chain lengths. So it's commonly reported in weight fraction. That's the more common way to do it. Okay? So let me ask you this. Why, in this plot, you see that weight average is over here, but number average is over there. Why are those not the same thing? Why are we reporting different numbers? So turn to your neighbor and try and explain why it might be that weight average won't always be the same as number average. Okay, what do you think? Why might these things not be the same number? Anybody have a thought? Any ideas? Yeah.
Just because, like, the number, there might still be some, even though, like, most of them might be this length, there might be some of them that are much longer, that would weigh a lot more, and that would shift the
Bingo.
weight, molecular weight.
Yeah. So let's put this on a log axis for a minute. So these might represent the chains that have 1 million units in them. And there's not very many that make it to have that long of a chain. But if it's got 1 million repeat units, then it weighs a ton. So it doesn't matter if there's only a few weight percent. That could dominate, right? Because those weigh a ton. So even if there's only a few of those chains, there could be a lot. This one, maybe there's a whole bunch of these that only have 5 or 10 or 20 repeat units, but they don't weigh very much. Because 5 or 10 or 20 units doesn't weigh all that much. So that's going to shift this. Instead of them being lined up, it shifts the weight average towards the heavier chain lengths. Does that make sense? Heavier chains weigh more, and so it moves the weight average out a little bit. Okay? Any questions? Yeah.
I'm just a little confused on what each of those averages are. So, like, what is the number average?
Okay. So maybe let's talk about how you would measure them. If you were going to measure this, you would have a tool that could measure something in that range, right? In that range, maybe that's a speed at which your spindle is spinning in your viscometer. You could say, okay, things between this chain length and that chain length, we have 10 weight percent, right? But if you'd move next door, the next bucket over, maybe it can measure from there to there. This one measures from there to there. So each one of these buckets, if you will, each one of these ranges of polymer lengths, we could assign it a weight fraction, which would come from something like viscometry. But other techniques can also do this, right? So this might be 10 weight percent, 15, 20 weight percent, something like that. And if you added up all of these buckets, you'd get to 100 weight percent. Make sense? The catch here is that these ones, even though there's only 5 weight percent, by number, that might represent much more by weight, right? So if we have a tool that's counting by weight, then this MW would be centered in the middle. This plot must have been counted by number. They must have had a tool that counted strands, literally numbers of strands, as opposed to the weight of each strand. So viscometry wouldn't give you this curve, right? This curve came from something else, a different tool that counted strand length. Because the heavier strands, even though there's not very many of them, they're disproportionately contributing to the overall molecular weight. Okay? Yeah?
This may be further along in the slides, but what is the usefulness?
Okay, so yeah, we will talk more about this, but in general, you'd love to have a single chain length of polymers. If you had that, then your properties would be much more homogeneous. For example, these materials with low chain length versus high chain length, we've already seen that they melt and they boil at different temperatures. Well, what's going to happen if you've got a polymer that has a bunch of different ranges? What will happen to your melting point? What will happen? What will it look like? Will there be one melting point? Yeah, Josh, what do you think? Yeah, there's going to be a range at which it starts to melt because part of it is melting, but part of it's not molten. So instead of having like these nice, sharply defined thermal features, for example, you get this region. And the same happens with Young's modulus, hardness. all the properties you care about, instead of having nice, crisply defined properties, you get big variations, right? So why do we care about this is because we need to be able to understand what is the molecular weight, and more importantly, what's the range of molecular weights, because that will influence properties. Yeah, Jaden?
So does that mean the closer those two are together, the more homogeneous your mixtures or your polymer is?
So that's a good question. Those can't ever be close together because by definition, the way that we define these things, molecular weight will always be shifted to the right because heavier chains always weigh more than short chains. So they can't overlap.
But like as they get closer, does that mean it's more homogeneous?
No, the better way to think of it is as this curve goes from being a broad distribution to a really sharp one, where all of your chains exist at one chain length or one molecular weight. That's really good. That's desirable. So when you look in your bottle, anybody have a plastic something that says HDPE, LDP, something like that on it? Next time that you're around a bottle at home or a Tupperware, take a look at it. If it says HDPE, that stands for high density polyethylene, those tend to be, it means that instead of having this nice broad distribution where you've got the short molecular weight, which leads to low density, they've somehow separated this stuff out and they have just the high length stuff, which leads to higher strength, better modulus. You'll even see UHW, ultra high molecular weight polyethylene, UHW, HDPE. So any of those numbers, the letters you see before the PE, they're trying to tell you something about the molecular weight. A better tool would be just to tell you the molecular weight, but we can't imprint that on the back of a bottle very easily. But we can put that on a spec sheet. So when you buy polymers, you'll want to look at what is the molecular weight of these things and what's the distribution. And hopefully, if it's a good provider, they would even give you a curve like this so you know exactly what to expect. Okay?
Does it tell you something based on the distance between the two? Like, is that a valuable?
So maybe I'll turn around the question to the audience. What would it mean if the separation distance was huge versus small between Mn and Mw? What does that imply about the type of polymer that you have? Yeah, so, well, Alex might have it. Anybody think they understand this? If there's a big, big difference between the weight average and the number average, what does that imply in the back? You guys are getting close. Let's compare this one for a minute. The repeat unit, right, of this is massive. You could add up all the weights of these things, right? 6 carbons and 6 hydrogens there. There's 2, 3 oxygens. You could add up all those things. And the monomer weight, we call this the mer weight, right? The weight of the mer unit that repeats is really high. So even though your chain length might be like there's a certain number of them, each one of those weighs a ton. That's going to lead to a bigger difference between your weight average because each one of these mer units weighs a ton. So it's going to move your molecular weight further over, if that makes sense. So bigger mer units will lead to a bigger separation. That's all that means.
So the longer the strand, the bigger the separation between.
Well, when we say longer the strand, I'm talking about if you're saying the longer the repeat unit, then yes. Yeah, not the total length of the strand, because the strand is made up of many of these repeat units. If this is a big repeat unit, then it'll have a big difference between the two. Yep. Okay, so how do we calculate these things? We just take averages is one way. Yeah, question? Yeah. Yep. Yeah, it's like reporting. They're just two different measures of a material because one gives you the weight fraction based off of the weight of the molecule, and one gives you the weight or the number fraction based off of the number of molecules of that length. So they're complementary measurements. So this is the mathematical definition. The weight average, right, the molecular weight is you sum up all the different buckets of weight that you can measure, between 0 grams per mole and 100 grams per mole. What weight fraction do you get, right? And you'd add that up for all the different buckets at which you can measure them by weight. Or you could do the exact same thing, but instead you do it by xi for number, where xi is the number fraction. And again, different characterization tools will give you different measurements, right? Viscometry will give you one, but there's other measurements that will give you another. And I'm not a polymers person, so I actually don't know what those are. But I know that they exist. Okay, a useful measure that is also commonly reported on a spec sheet is to say what the degree of polymerization is. I think this is the most useful measure, maybe, degree of polymerization. You take the average molecular weight and you divide it by the mer weight. So m with the bar on it, on top, the little m with the bar, that's the weight of each repeat unit, the smaller section. This big M with the bar on it, that's your average molecular weight. So if you take the total molecular weight, meaning the weight of the entire chain, if it's a million grams per mole, but each repeat unit is only 20, then you would take 1 million, divide it by 20, and that would give you the degree of polymerization. And you can do this on a per weight basis or a number basis. Okay? So this is useful. The degree of polymerization on a number basis tells you how many repeat units are on the chain. Is it 100,000 repeat units? Is it 50? Right? That's what this n sub n will tell you. Or you could do it based off of weight as well. Okay? Any questions on this? We'll do an example in just a minute where we actually calculate this. Now, if you have more than one mer unit in your chain, like nylon 6,6, you could treat the whole thing as one mer unit, the whole nylon 6,6 repeat unit, or you could treat those as two separate units, right? The first 6 carbon chunk and the second 6 carbon chunk. And if you do that, then you have to basically just break it up into a fraction. You say half of it corresponds to the first monomer, half of it corresponds to the second monomer. So you see this new expression that your mer weight is equal to the contribution of each individual mer multiplied by the fraction of them that's present. So let's imagine we made a new polymer today. We made a new polymer, and it's like nylon 6,6, but now it's nylon 6,6,4, right? So you've got the first part of the 6,6, which has the double bonded oxygens, and then it's got the amine group, right? Then you've got your other 6, and then it's got the other amine group. And then we made another one, right, which only has 4 carbons on it. And this is the thing that gets repeated, right? If that's what we created in our lab somehow, if you wanted to figure out the mer weight of this whole thing, you'd just add it all up, right? Or if you wanted to treat it on a per mer basis of each one of these, treating them separately, like this is your A monomer, this is your B monomer, and that's your C monomer, then it would be 1/3, 1/3, 1/3 each, right? That's what this F fraction is corresponding to. It's what fraction of your mers. Maybe you have something funny. Maybe you have like 2 of these repeat ones in a row, and then this one, right? So then this would be 0.66 of this and 0.33 of that, right? This is one of the exciting things about polymer science, is that you can make so many crazy different combinations of polymers, because you can just change out the type of mer units you want, right? Instead of having it be really simple, like polyethylene, which is the same repeat unit, you can start plugging in all sorts of crazy side groups. Maybe you only want a little bit of something, but it adds a little bit of a good property, like it absorbs UV light. You don't need a ton of it. You just need a little bit to absorb the UV light to protect the rest of the chain, right? You can start making really interesting polymers by forming copolymers of different mer species. Okay, so let's do an example here. It says, this is going to be a clicker question. It says, which of the following has the highest average degree of polymerization if the number average molecular weight for all 4 of these is equal to 254,000? Which one has the highest average degree of polymerization, meaning the largest number of repeat units? The total chain length from end to end, it weighs 254,000. That should be grams per mole. So which one has the highest degree of polymerization? To go about answering this problem, we're going to say that n sub n equals our average molecular weight divided by the mer weight. Okay? So if all 4 of these polymers have the same chain-to-chain total number average molecular weight, we just divide them by their mer weight to figure out which one has the largest number of repeat units in it. Okay? So give that a shot. So again, you're solving for n sub n. You want to figure out which one is largest. And to do that, you need to figure out which one of these Heaviest or lightest? For those that don't remember, carbon is 12, oxygen is 16, nitrogen's 14, hydrogen's 1, and chlorine is 35. Okay, what do you get? Is it the first, the second, the third, or the fourth that should have the highest degree of polymerization? Yeah, you're going to take whichever one, so they all have the same numerator, m sub n, the capital, that's your number average molecular weight. Whichever one divided by the smallest number will give you the largest number of repeat units. So you take that, divide it by 96, and what do you get? What number is that? 250,000 divided by roughly 100 is how many repeat units? Yeah, around 2,500 repeat units. This makes sense how we go about this? So if I gave you on a test, I said this is the monomer unit. It has a degree average polymerization of 50. What's the molecular weight? Then you'd do this in reverse. You'd say, okay, there's 50 of them. Each one weighs 96 or whatever it may be. You can figure out the chain length of that one, okay? Any on this? These are just convenient ways to characterize the lengths of polymers. Yeah?
So, sorry, I think you just said it, but is degree of polymerization kind of like the length of the chain?
It's how many repeat units are in the chain, right? So if these are like Legos, and you keep on adding a Lego to make it longer, it's saying how many Legos are in the chain, in the total length. Yeah, Landon, did you have a question? Same thing. Other questions about this? Josh? Good question. If I didn't give you the monomer, you couldn't solve it. But let's say that and you could start, how could you do this? I could say, this would be maybe a good homework question. Let's say I said the same type of polymer has 3 distinct groups of chain lengths, okay? So it's the same monomer. So you know that the repeat unit's not changing. And if we said it's made up of 3 different elements, you could write 3 equations with 3 unknowns and solve for what the monomer has in terms of, say, carbon, hydrogen, oxygen. That's actually a good homework question. So more on that coming soon. Okay. Now, like I said, in the real world, we would love to have a polymer chain that's just, everything is the same length. That means it's going to have nice, crisply defined properties. And we can't get that. But there are some things that we can control in the laboratory to influence chain length, molecular weight. Temperature, the amount of radical catalyst, and then the rate of polymerization. That's largely tied to your temperature, right? Those things can influence it. For example, if you let things happen really slowly, then you might end up with longer chains overall, as opposed to really rapidly, where they might just find a shortcut chain very quickly, right? Really, though, the big thing that you can control is the amount of radical, right? Adding lots of it means shorter chains. Smaller amounts of it means longer chains. Because, again, it just means there's more of these things that can find each other from start to end. Okay? Some rules of thumb that you should be aware of goes as follows. If the molecular weight of your polymer is less than 100 grams per mole, then it's a liquid, right? This is things like alcohol, right? Alcohol is a liquid because it's a pretty short molecule. It's not very long in terms of that. Most of the fuels that you put in your car, right? Octane, right? Benzene. These things are typically liquids because they're small molecules. If you start getting larger, now you're on the order of, say, 1,000 grams per mole, the total length of your chain, it transitions to a solid, but it's what we call a waxy solid. So beeswax, this would be an intermediate chain length. It's not super long. And as you get really, really long chain lengths on the order of 10 to the 5, maybe 10 to the 4, now you start getting solids. We call these high polymers, right? So the stuff that you're going to make things out of, if you want it to be rigid, right? Like this mouse casing, you want it to be pretty strong. You would not use a low molecular weight polymer because it would be soft. It would scratch easily. It would be flexible. You'd probably want it to be a little more rigid, so you'd use a higher molecular weight polymer. Yeah, Alex?
When you say per mole, that's like moles of chain.
Yeah. Normally, great question. In chemistry, you talked about moles of per atom sometimes, and sometimes per molecules. Polymers are just really big molecules, right? Sometimes we call them macromolecules. They're really big molecules, right? Because they can be 100 or 1,000 units long, but they're still just molecules. So it's still, the mole calculation still works. But instead of calculating on a per atom basis, it's per moles of substance, right? Which can be long chains. Any questions about that, these general rules of thumb? Okay. Shape makes a big difference, right? We've shown you so far that the chain zigzags, right? Our chain looks something like this. Somebody remind me, why does it zigzag? Yeah, so these are they're typically carbon. We've seen examples where it's not carbon, right? You can stick an oxygen there. An oxygen will almost always form a linear chain length as opposed to this kinked one. You can put a benzene there. That makes it linear over the whole benzene ring, right? But most of these are kinked like that because they're carbons. And carbon wants to form 4 bonds, unless it's double or triple bonded. But when it forms 4 bonds, the optimal separation distance, this angle right here, is 109.5 degrees. That right there is 109.5 degrees, okay? So if you wanted to calculate the total chain length, which comes up occasionally, when you stretched it out, first off, when you stretch it out, you get rid of the kinks, right? Those those come from bonding, so they're very difficult to stress. When we stretch it out, all we're meaning is we basically line this up exactly like it's drawn like that. Okay? And what would be this total length? What would the geometry be? Well, it's given right there. And you can figure this out yourself. If you want to know this distance right here per mer unit, and you know this angle right there, and you know this length right here, then you know that, let's define these things. Let's call this right here D, that bond to bond length, a carbon bonded to a carbon. If we know that length, and it's D, so that's the hypotenuse of this triangle. This is a 90-degree triangle right here. So this angle, the sine of this half angle is equal to the opposite, that's the thing we want to know, divided by the hypotenuse. That's what we know, right? So that's where this equation comes from. ND sine theta will give you the length of this, where N is the number of these repeat units, or the number of these bonds, not to be confused with the number of mer units, right? This thing is all one mer unit, and sometimes we call that N, small n. Big N is how many bond lengths are present in that, right? Let's do a simpler one first. Let's do this one. So small n is how many repeat units of this there are in the total chain. But in each one of these repeat units, how many bonds are there? We could count them. So here's a half a bond. So we'll get to that in the end. We've got 1 bond, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 14 if you include the halves on the end. So there are 14 carbon-carbon bonds, except they're not all carbon-carbon bonds. Some of them are carbon-nitrogen, right? There's 1, 2, 3, 4 carbon-nitrogen bonds and 10 carbon-carbon bonds in here. Make sense? So if I asked you to tell me if this polymer is stretched out, what's the total length of it, how would you go about it? Well, first off, you'd have to account, there's, if we're doing nylon 6,6, let's do that one real quick. If I told you that N is equal to 50, so there's 50 mer repeat units, and inside each mer, N is equal to 14 bonds, 4 of which are carbon bonded to nitrogen, and 10 of which are carbon bonded to carbon, right? The next thing that you need to do is figure out what are the bond angles on those. Now, I have no idea what the bond angle is for nitrogen. I think that it forms a planar bond. It's trigonal planar, I'm pretty sure. If we go back up to this, I'm almost positive that nitrogen only forms 3 bonds. So instead of being that tetrahedral, which leads to the 109.5, this is 120 degrees. I'm almost positive. So technically, you'd have to take those things into account if you wanted to figure out the length of these. Or you could just do a back-of-the-envelope calculation and assume that all these are basically carbon-carbon with 109.5, and it's not going to be that far off, right? Technically, you could solve it exactly. If I said that this angle is not 109.5, but 120, you could account for that, and you could solve this, okay? Are there any questions about this? Figuring out the length of these things? Alex?
For the nitrogen one,
Or Alan?
it's still 109.5, it's just they didn't mark the lone pair there.
Oh, they didn't mark the lone pair. Good call. I'll bet that changes it. I'll bet it's not exactly 109.5. Yeah, thank you, Alan. You're right. Any questions about this? So some bond lengths that you should know. I think I've got it written here. Okay, right here. Carbon-carbon bond lengths. This you should just put on your note sheet. If it's a carbon-carbon single bond, its length is 1.54 nanometers. About, right? Sorry, 1.54 angstroms, 0.154 nanometers. Excuse me, I said that wrong. It's written here correctly, 0.154 nanometers or 1.54 angstroms. Okay? Any questions on calculating how long these things are? Yeah? Theta is the bond angle, right? So for example, if this is carbon-carbon, that's this 109.5, and they divided it by 2 because we are doing each segment at a time. That's where that came from. Okay? Any questions on this? This is sort of 9th grade geometry that you learned about, now just applied towards engineering stuff. Okay, now it's uncommon for polymers to be lined up like that. You can make specialty polymers that do line up like that. Kevlar is a great example. Nylon fibers tend to be pretty good examples of that. They tend to line up. Ultra high weight polyethylene, high molecular weight polyethylene, they tend to line up for bonding reasons. But for many times, that's not the case. They can be lined up if you were to grab them with tiny tweezers and stretch them out, but that's not what happens. Instead, they crinkle up, just like a ball of spaghetti, right? Spaghetti can twist and rotate. Polymers do the exact same thing. What you'll notice, though, is that along each one of these kinks, this stays 109.5 if it's carbon bonded to carbon. But each one of these things, because they're single bonds, each one of these things can rotate in that cone, right? Now, a double bond can't rotate. It's fixed, but a single bond can rotate. So what that leads to is there's lots of uncertainty. You can actually make this thing wind up in lots of different ways. If you went end to end and you counted all these things up, they could make all sorts of kinks and turns along the way. But the overall size of the macromolecule, you could assign it a distance, right? Basically like the radius of this thing, we could give a number to that. And there turns out to be a decent way to estimate it. It's r, the radius of this agglomerate of molecules, is going to be d, that's your bond-to-bond distance. If it's carbon, that's 1.54 angstroms, multiplied by the number of these chain lengths. Well, not chain lengths, bond lengths, right, along the chain. Yeah, question?
What determines, like, at what angle it's going to, like, rotate?
Yeah, good question. The question was, what determines this angle here? Oh, okay, so which one of these, there's 360 degrees possible. What determines it? What do you guys think? That's a great question. What should determine that? You've got, anytime there's a question on why something happens, what are our two answers? You know it's either related to enthalpy or entropy. So what does entropy want? Entropy wants this as most random as possible. It wouldn't want it, say, in an alternating pattern, because that is ordered to some degree, right? Straight in a line is the worst of all. That's the most ordered you can get. Alternating's a little bit better, but it's still worse than random. So entropy is saying, make it as random as possible. In the real world, we don't get that. It's somewhere in between or sometimes lined up, which means enthalpy must be playing a role. And anytime I say enthalpy in this class, what am I talking about? It's bonding, right? Bonding. So if your molecule, let's go up to something like nylon. Let's go up to nylon again. It's a good example. Take a look at nylon. Nylon, you've got these groups with the double bonded oxygen, and then you've got these amine groups with this hydrogen here. What do you think is going to happen when I put another chain of nylon in vicinity of nylon 6,6? What might happen? Exactly. You're going to get hydrogen bonding between these groups and those groups when they line up to each other. So that tends to make them more linear because they want to line up to maximize the number of those secondary bonds, hydrogen bonds in this case, right? So the types of groups on it, to your question, what dictates how these things basically come together? It often is dictated by side groups or functional units that might want to line up to bond, right? In this case, they want to line up in nice lines so you can get as many of these bonds, like from another chain, the amine group would bond to this oxygen as possible, which makes it a strong. Kevlar does the same thing. Kevlar is a really strong fiber because it has secondary bonding that's fairly strong between the molecules and really strong in the chain. Okay, yeah, question, Jaden?
So they still can't be like tangled and like out of order with those bonds. Like couldn't you have like both those strands that have the hydrogen bonds on them be very?
Yeah. So this maybe leads to a next thing that we can get is you can get elastomers. Actually, we're perfect timing, Jaden. Let's say you've got a polymer like this, okay, and you've got another polymer in the vicinity doing its thing, but then you introduced a little bit of sulfur to this, and the sulfur, in rubber at least, acts as a cross-linker. It can literally form, instead of a weak secondary bond like a hydrogen bond, which is not that strong, it can put a strong covalent bond, right? So if you put something that can form additional bonds than just the 4 that carbon expects, like sulfur in here, which can form 6 bonds, right? All of a sudden, this can link together different chains. So when they make rubber tires, this was the whole amazing invention that Goodyear, on total accident, was cooking polymer rubber on his stove. He accidentally spilled some sulfur in there. He mixed them on total fluke accident, and you get cross-linking. So think about what that would do. Now you've got these chains. Normally, they want to twizzle together, right, and form like these spaghetti balls. And as you start to stretch them, they can slide past one another. But if you've got one of these, a strong bond, a covalent bond, it can't just slide past each other anymore. This bond starts getting stretched. All these bond angles, which want to be 109.5, when you stretch it, they all can give a little bit, but you're storing elastic energy in the molecule. And all of a sudden, you've got rubber. You've got elastomers, which are materials that can absorb, they can store lots of energy because there might be hundreds of thousands of these bond lengths in them. So even though each one only stretches by a degree, that over 100,000 can be a whole bunch, and you've got these things holding them together. So you only have to add a very small amount of sulfur, cross-linker, and you don't have to, it doesn't have to be sulfur, it can be other things. A small amount of cross-linker will actually impart a huge amount of elastic energy, so you stretch it, but then it wants to snap back because it can't break and slide. That makes sense? So that's the role of cross-linking. So when you see elastic response like elastomers and rubbers, that's what's happening, is they've put a few covalent bonds connecting these things when otherwise there'd just be weak secondary bonds holding them. Now there's lots of different types of structures that can form. You can have no side groups. You can have really long side groups that form long branches. Yeah, question?
Sorry, going back to the end-to-end distance
Okay.
a little bit, is that like the physical distance between the one end?
Okay, so let's assume that it's not cross-linked, so it's just a jumble. It's a spaghetti bowl. It's basically like the size of your spaghetti bowl, right? It's how big is like the jumble of particles. I think it's actually a radius. Oh no, end-to-end distance is r. Sorry, that's end-to-end.
Okay, so that's if you like stretch it out, that's how long it is.
Oh, no. End-to-end, meaning the beginning of the polymer to the end of the particle, polymer. Which is a good proxy for how big of a sphere the macromolecule would form, right? That's that small r. So we talked about linear, branch, cross-linked. We talked about network. That's things like bakelite that can form bonds in more than two directions. If it can bond in a third direction, like bakelite does, that's why it makes such a really strong, hard polymer, because the chains can't slide past each other because it's bonded in 3 dimensions. It looks more like a ceramic or like materials that we're otherwise familiar with. Now, each one of these repeat units, they can also connect in a variety of different ways. This is why polymers are so interesting. There's just so much complexity here, right? You've got, let's say that this is your repeat unit. You've got it looks like polyethylene, but it's got one functional group, which they're just calling R. That could be a methyl group, and you get polypropylene. It could be a chlorine, and you get polyvinyl chloride, PVC, right? But it's just R for a minute. They can connect head to tail, head to head, or tail to tail, right? These can connect in lots of different ways. Obviously, the entropy would say make it as random as possible. But if it's ordered, maybe there's a bonding reason why that would happen, okay? So these can be you can think of these kind of as defects. What if you just have one of these switched from what it would normally be? That's like a point defect in the polymer. It's something that's out of place. All next chapter is going to be on point defects and other types of defects in materials. You also get isomers, like stereoisomers. Take this one. You can have isotactic. Iso means the same, tactic means side. Everything is on the same side. This is polystyrene, where polystyrene, all the styrene groups, right, are all on the same side. Or they could be alternating, that's syndiotactic. Or they can just be random, atactic, right? We could go on. Like these things, if there's a double bond, they can connect on the same side of the bond. We call this cis. Or on opposite sides of the bond, that's trans. There's just a few more words, so we'll pick this up next time because we're out of time. So get ready for next chapter. We'll talk about chapter 5. The midterm scores are posted. The midterm solutions are up. You can pick up your exams in my office anytime.